In the depths of space, where silence reigns eternal, exists a tranquility so profound it defies human comprehension. Tonight we embark on a journey not of destruction, but of healing. Not of violence, but of peace. We will drift through cosmic sanctuaries where time moves differently, where the very atoms that compose your being remember their stellar birthplace, and where the infinite expanse offers a perspective that can transform the deepest anxieties into profound calm. Close your eyes. Feel your breathing slow. We begin our ascent into the healing embrace of the cosmos. Deep within every cell of your body, a microscopic universe unfolds in perfect harmony. Electrons orbit atomic nuclei in quantum clouds of probability, never touching, never colliding, existing in a state of pure potential. These subatomic particles dance to rhythms older than Earth itself, following laws that have remained unchanged since the first moments after creation. The calcium in your bones was forged in the dying breath of ancient stars, compressed under pressures that could crush mountains, then gently released into the cosmic wind to eventually find its way to you. Every atom in your body has traveled billions of miles through space and time to be precisely where it is right now, in this moment, creating the temporary arrangement of matter that is uniquely you. Your carbon atoms once resided in the heart of a massive star, participating in nuclear fusion reactions that released the very light that warmed primordial worlds. The oxygen you breathe was created when these stellar giants finally exhausted their fuel and gently expelled their enriched atmospheres into space, seeding the galaxy with the building blocks of life. Think of this: you are not separate from the universe. You are the universe expressing itself in conscious form. The iron in your blood carries the memory of cosmic violence transformed into life-giving flow. The hydrogen in your water molecules remembers the first 3 minutes after the Big Bang, when the universe was a soup of pure energy cooling into the first atomic nuclei. The quantum realm operates on principles of uncertainty and possibility, rather than rigid determinism. At the smallest scales, particles exist in superposition, simultaneously in multiple states until observation collapses them into a single reality. This quantum flexibility mirrors the human capacity for change, growth, and transformation. Just as particles can tunnel through seemingly impossible barriers, your consciousness can transcend the limitations that seem absolute. The empty space between your atoms contains quantum fields that permeate all existence, connecting you to every other piece of matter in the universe through invisible threads of energy. These fields carry information instantaneously across vast distances, creating a web of connection that spans from the smallest subatomic realm to the largest galactic structures. When anxiety overwhelms your mind, remember that your atoms remain perfectly stable, following natural laws that have guided matter since the beginning of time. The quantum fields within you continue their eternal dance, indifferent to the temporary storms of thought and emotion. You are anchored to the cosmos by bonds stronger than any terrestrial concern. Scattered throughout our galaxy are celestial lighthouses called pulsars, neutron stars that emit beams of radiation with clockwork precision. These cosmic metronomes maintain timing so accurate they rival the most sophisticated atomic clocks humans have ever built. PSRJ 1713 plus 0747 has kept perfect time for over 2 decades, losing less than a millionth of a second. Imagine synchronizing your breathing with one of these distant pulsars, let's say PSRB 1919 plus 21, the first pulsar ever discovered. Every 1.337 seconds, this stellar lighthouse sends its gentle beams sweeping across space. As you breathe in, the neutron star completes nearly a full rotation. As you breathe out, its magnetic field channels particles into a focused ray that has been traveling toward Earth for centuries. These pulsars are not destructive forces, but cosmic meditation bells, marking time with perfect regularity across the galaxy. Their pulses have been travelling through space since before your ancestors first looked up at the stars, carrying a message of consistency and reliability through the apparent chaos of the universe. The neutron star at the heart of each pulsar represents matter in its most stable possible form. Atomic nuclei packed so tightly they create a uniform crystalline structure. This is matter that has found its perfect equilibrium, neither expanding nor contracting, existing in a state of absolute balance between the forces that shape reality. As these stellar meditation timers pulse their rhythm across space, they demonstrate that even the most extreme objects in the universe can achieve perfect harmony. A neutron star contains more mass than our Sun, compressed into a sphere smaller than a city, yet it maintains this incredible density with serene stability for billions of years. The magnetic fields surrounding pulsars create invisible structures of incredible beauty, geometric patterns that would appear as glowing sculptures if we could see magnetic field lines. These fields guide charged particles in spiraling dances, creating aurora-like displays that stretch for thousands of miles around the neutron star. Some pulsars exist in binary systems, orbiting companion stars in gravitational waltzes that demonstrate the universe's capacity for partnership and mutual support. These stellar couples have maintained their cosmic dance for millions of years, each partner's gravity providing the stability the other needs to continue existing. Let the steady pulse of distant pulsars become your breathing rhythm. Feel your heartbeat synchronize with cosmic clockwork. Allow the reliability of these stellar lighthouses to remind you that beneath all temporary turbulence lies an underlying order that has persisted for billions of years and will continue long after any current concerns have faded into memory. In the spaces between stars, vast clouds of gas and dust drift like cosmic gardens, slowly nurturing the birth of new stellar generations. These nebulae are not empty voids but fertile nurseries where matter condenses over millions of years into the brilliant points of light that will illuminate future worlds. The Eagle Nebula, 7,000 light-years away, contains pillars of creation where new stars are being born at this very moment. These towering columns of gas and dust stretch for light years, their surfaces sculpted by gentle stellar winds into formations of breathtaking beauty. Within their dense cores, gravity works patiently to gather material until nuclear fusion ignites, transforming cold matter into warm, life-giving light. The Rosette Nebula blooms like a cosmic flower 65 light-years across, its petals formed by the delicate interplay between stellar radiation and interstellar matter. At its heart, young, massive stars create a cavity in the surrounding gas, not through violence, but through the gentle pressure of their light, carving out a space where smaller stars can form in peace. These stellar nurseries operate on timescales that dwarf human anxiety. A typical star formation process takes 10 million years, a duration that makes our personal struggles seem like brief flickers in cosmic time. The nebulae demonstrate patience in its purest form, allowing natural processes to unfold at their own pace without forcing or rushing toward completion. The Helix Nebula, sometimes called the Eye of God, spans nearly 3 light-years and represents a star's gentle transition from main sequence burning to planetary nebula. When Sun-like stars exhaust their nuclear fuel, they don't explode violently, but instead gracefully shed their outer layers, creating expanding shells of glowing gas that will eventually disperse to enrich the interstellar medium for future generations of stars. Within these cosmic gardens, temperature and pressure change gradually across vast distances. Gas that is scorchingly hot near young stars cools to just a few degrees above absolute zero in the outer reaches, creating environments where different types of molecules can form. Complex organic compounds, the building blocks of life, condense in the cooler regions, seeded throughout space like cosmic fertilizer. The colours of nebulae tell stories of gentle atomic processes. Hydrogen glows red when excited by starlight, oxygen shines blue-green, and sulfur produces golden hues. These are not harsh, overwhelming colours, but soft, diffuse glows that paint space in pastel shades reminiscent of sunset or aurora. Some nebulae, like the Cat's Eye Nebula, display intricate geometric patterns created by magnetic fields and stellar winds interacting over thousands of years. These cosmic mandalas demonstrate that even in the vastness of space, natural forces can create structures of perfect symmetry and balance. As you visualize these stellar gardens, imagine your thoughts as wisps of cosmic gas, slowly condensing and organizing into new patterns. Allow the patient timescales of star formation to put your immediate concerns into perspective. The nebulae remind us that growth and change often happen slowly, almost imperceptibly, but with inevitable beauty. Beyond our solar system, thousands of exoplanets orbit distant stars in gravitational harmonies that demonstrate the universe's tendency towards stability and balance. These planetary systems have achieved orbital resonances so precise they maintain their delicate dances for billions of years, each world contributing to the gravitational symphony that keeps the entire system stable. The TRAPPIST-1 system, 39 light-years away, contains 7 Earth-sized planets locked in a chain of gravitational resonances. For every 8 orbits of the innermost planet, the second completes 5 orbits, the third completes 3, and so on in a mathematical progression that ensures the system remains stable despite having 7 worlds packed into a space smaller than the orbit of Mercury. These orbital resonances create what astronomers call gravitational music, periodic variations in planetary motion that repeat in complex rhythms spanning thousands of years. The planets are essentially playing a cosmic symphony, each world contributing its own gravitational note to a harmony that emerges from the mathematics of celestial mechanics. Kepler 223 displays a perfect 4-planet resonant chain, where the orbital periods form precise mathematical ratios, 3:4 to 6:8. This system has maintained its harmonic configuration for billions of years, demonstrating that even complex gravitational interactions can achieve and maintain perfect balance over cosmic timescales. Some exoplanets orbit in the habitable zones of their stars, regions where liquid water could exist on planetary surfaces. These temperate worlds represent cosmic sanctuaries where the conditions necessary for life exist in stable equilibrium. The star provides just enough energy to maintain moderate temperatures, while the planet's atmosphere and magnetic field create protective shields against harmful radiation. HD 40,307 grams orbits a quiet red dwarf star at precisely the right distance to maintain Earth-like temperatures for billions of years. Red dwarf stars burn their nuclear fuel so slowly they can remain stable for trillions of years, far longer than the current age of the universe. Planets in these systems have the luxury of geological timescales measured not in billions but in trillions of years. The discovery of super-Earths, planets larger than our world but smaller than Neptune, reveals that the universe contains many variations on the theme of planetary existence. Some of these worlds have thick atmospheres that create gentle greenhouse effects, maintaining warm temperatures even at greater distances from their stars. Others have extensive ocean systems that could remain liquid for cosmic ages. Binary star systems create even more complex gravitational environments where planets can exist in stable orbits around both stars or in figure 8 patterns that thread between the stellar pair. These circumbinary planets experience double sunsets and navigate gravitational fields of incredible complexity while maintaining stable orbits that can persist for billions of years. The moons of exoplanets add another layer of gravitational harmony to these distant systems. Large moons stabilize planetary rotation, preventing the chaotic tumbling that could make worlds uninhabitable. They create tidal forces that could drive geological activity, maintaining planetary magnetic fields that shield atmospheres from stellar wind erosion. As you contemplate these distant worlds, imagine your own life as a planet finding its stable orbit. Sometimes you may feel pulled by competing gravitational forces, responsibilities, relationships, ambitions. But remember that planetary systems demonstrate how multiple influences can create stability rather than chaos when they achieve the right balance. The exoplanets remind us that the universe is filled with worlds, each following its own path through space and time, each contributing to the gravitational harmony of its system. You too are part of a larger system, family, community, species, planet, and your presence contributes to the stability of the whole. Our Milky Way galaxy rotates with majestic slowness, completing one full revolution every 225 million years. This galactic year provides a timescale so vast it renders human concerns momentary. The last time our solar system occupied its current position relative to the galactic center, the first dinosaurs were just beginning to evolve on Earth. The galaxy's spiral arms are not rigid structures, but density waves that move through the stellar disk like slow-motion traffic jams in space. Stars enter and exit these arms over millions of years, experiencing periods of increased star formation when they pass through the denser regions, then returning to quieter phases in the spaces between arms. At the galactic center, instead of the destructive black hole often imagined, lies Sagittarius, a star in a state of relative quiescence. This supermassive black hole, containing 4 million solar masses, currently accretes matter at a rate so low it barely glows in radio wavelengths. It serves not as a cosmic destroyer, but as a gravitational anchor that holds our galaxy's billions of stars in their stable orbits. The galaxy contains ancient stars that have been burning steadily for over 12 billion years, nearly as long as the universe itself has existed. These stellar elders have witnessed the galaxy's entire evolutionary history, from its chaotic early days through its current mature spiral structure. Their continued existence demonstrates that stability and longevity are possible even in a dynamic, evolving universe. Between the spiral arms lie vast regions of space where star formation proceeds slowly and gently. These are the galaxy's suburbs, quiet neighborhoods where older stars orbit peacefully, some harboring planetary systems that have remained stable for billions of years. Our solar system spends most of its galactic orbit in these tranquil regions. The galaxy's halo contains globular clusters, ancient stellar cities where hundreds of thousands of stars orbit in perfect gravitational harmony. These clusters are among the oldest structures in the galaxy, having formed when the Milky Way itself was young. They demonstrate that even gravitationally complex systems can achieve and maintain stability over cosmic timescales. Dark matter provides the invisible scaffolding that holds the galaxy together, creating a smooth, stable gravitational field that allows stars to maintain their orbits without being flung into intergalactic space. This dark matter halo extends far beyond the visible edge of the galaxy, creating a protective cocoon that has preserved the Milky Way's structure for billions of years. The galaxy breathes on a timescale of hundreds of millions of years, with star formation rates rising and falling in response to external influences like minor galaxy mergers or passages through the local group's gravitational field. These are gentle fluctuations in the galaxy's metabolism, not catastrophic disruptions. Stellar streams, rivers of stars torn from small companion galaxies, flow through the Milky Way's halo like cosmic auroras, adding their stellar populations to our galaxy's family. This process of galactic growth happens so gradually that it barely affects the existing stellar populations, demonstrating the universe's capacity for gentle, non-destructive change. The galaxy's magnetic field, though incredibly weak by terrestrial standards, extends throughout the galactic disk and helps regulate star formation by affecting the motion of charged particles in interstellar space. This galactic magnetosphere creates an environment where cosmic rays are channeled and moderated, contributing to the stability needed for complex chemistry and biology. As you contemplate the galaxy's deep time, allow your personal timeline to expand. Your life, your concerns, your aspirations are all embedded within this vast cosmic context. The galaxy has been pursuing its stately rotation for billions of years before you existed, and will continue for billions of years after your atoms have been recycled into new forms. This perspective can transform anxiety into awe, urgency into patience, and isolation into connection with something infinitely larger than personal circumstances. Surrounding us on all sides is the oldest light in the universe, the cosmic microwave background radiation that has been travelling through space for 13.8 billion years. This ancient glow fills every cubic centimetre of space with photons that carry information about the universe when it was only 380,000 years old, long before the first stars formed. This cosmic background represents the universe at its most serene moment, the instant when space became transparent to light for the first time. Before this moment, the universe was so hot and dense that photons could not travel freely. Matter and energy existed in perfect thermal equilibrium, with no structures larger than atomic nuclei. It was a time of absolute unity, before gravity had time to create the cosmic web of galaxies and galaxy clusters we see today. The temperature of this background radiation is precisely 2.725 Kelvin, just 2.725 degrees above absolute zero. This represents the universe's base temperature, the thermal foundation upon which all other temperatures are built. Every object in space that is not actively heated by nuclear fusion or gravitational compression eventually cools to this cosmic background temperature. The remarkable uniformity of this radiation in all directions demonstrates that the early universe existed in a state of nearly perfect equilibrium. Temperature variations across the sky are less than 1 part in 100,000, revealing that the cosmos began in a condition of extraordinary smoothness and balance. The tiny fluctuations that do exist became the seeds from which galaxies and galaxy clusters eventually grew. This ocean of ancient light carries with it a profound sense of cosmic democracy. Every region of space, no matter how apparently empty, contains thousands of these primordial photons in every cubic centimetre. You are constantly bathed in light that is older than the Earth, older than the solar system, older than most of the stars you see in the night sky. The cosmic background radiation serves as the universe's memory, preserving in exquisite detail the conditions that existed when space first became transparent. Scientists can read this radiation like a cosmic archaeological record, extracting information about the density of matter, the rate of expansion, and the fundamental parameters that govern reality itself. As the universe has expanded, this background radiation has been stretched to longer wavelengths and cooled from the brilliant orange glow it had at emission to the microwave radiation we detect today. This cosmic redshift demonstrates the universe's expansion in the most direct way possible. We can literally observe space stretching the wavelength of ancient light. The isotropy of the cosmic background, the fact that it has the same temperature in all directions, provides a unique reference frame for cosmic motion. The local group of galaxies, including our Milky Way, moves at 627 kilometers per second relative to this cosmic rest frame, creating a tiny Doppler shift in the background radiation that allows us to measure our motion through the universe itself. This ancient light connects you to the moment when atoms first formed, when the universe made the transition from an opaque plasma to a transparent medium through which light could travel freely. The photons warming your skin from this cosmic glow were present at that moment of cosmic clearing, witnesses to the universe's emergence from its primordial fog. During meditation on cosmic scales, imagine yourself floating in this ocean of ancient light. Feel the gentle warmth of photons that have been traveling for nearly 14 billion years to reach you at this moment. Allow the perfect uniformity of this cosmic background to represent the underlying unity that connects all regions of space and all moments in time. The cosmic microwave background reminds us that despite the apparent complexity and chaos of the modern universe, everything began in a state of nearly perfect simplicity and harmony. The elaborate structures we see today, galaxies, stars, planets, and life itself, are all elaborations on this original theme of cosmic unity. In the gravitational fields created by any two massive bodies, there exist 5 special locations where the competing forces balance perfectly, creating islands of stability in the ocean of space. These Lagrange points represent cosmic equilibrium, places where a small object can remain at rest relative to both massive bodies without being pulled toward either one. The L1 Lagrange point between Earth and Sun lies 1.5 million kilometers from Earth in the direction of the Sun. Here, a spacecraft can maintain a constant position relative to both bodies, using minimal fuel to make occasional small adjustments. This is where the Solar and Heliospheric Observatory, SOHO, has been stationed for over 2 decades, maintaining its vigil as it monitors solar activity. L2, located 1.5 million kilometers from Earth in the direction away from the Sun, provides an even more stable environment. The James Webb Space Telescope now resides at this point, where it can observe the universe in infrared light while remaining in constant communication with Earth. The gravitational forces of Earth and Sun combine to create a natural parking orbit that requires almost no energy to maintain. The L4 and L5 points, 60 degrees ahead of and behind Earth in its orbit, demonstrate nature's tendency toward triangular stability. These points have captured asteroids called Trojans that share Earth's orbit around the Sun while maintaining their positions in the most stable Lagrange points. Some scientists have proposed establishing space colonies at these locations, taking advantage of their natural gravitational equilibrium. Jupiter's Trojans number in the hundreds of thousands, creating 2 swarms of asteroids that have maintained their positions at the L4 and L5 points for billions of years. These cosmic archipelagos demonstrate that Lagrange points can provide long-term stability even in the complex gravitational environment of the outer solar system. The gravitational balance at Lagrange points creates a sense of weightlessness different from free fall. Instead of continuously falling toward a massive body, objects at these points experience forces from multiple directions that cancel out, creating regions of true gravitational neutrality. This is as close as nature comes to creating zones of perfect calm within gravitational fields. Some Lagrange points exhibit librational motion, gentle oscillations around the equilibrium position that resemble the motion of a marble rolling slowly in the bottom of a bowl. These movements are so gradual they take years to complete, creating a sense of cosmic breathing or gentle swaying that adds dynamic beauty to gravitational stillness. The stability of Lagrange points emerges from the mathematics of orbital mechanics, demonstrating that even in complex gravitational systems, natural balance points exist where forces achieve perfect equilibrium. These locations represent solutions to the three-body problem, one of the most challenging calculations in celestial mechanics. Binary star systems create their own networks of Lagrange points, some of which may harbour planets in stable orbits. These circumbinary worlds would experience the gravitational influence of 2 stars while remaining in regions of relative stability, creating unique environments where planetary systems can evolve over billions of years. The concept of Lagrange points extends beyond our solar system to any configuration of massive bodies. Every exoplanetary system contains its own network of gravitational equilibrium points, creating cosmic sanctuaries where matter can accumulate and remain stable over astronomical timescales. As you visualize these points of gravitational balance, imagine your own life finding its Lagrange points, places where competing forces in your experience achieve equilibrium. Like objects at L4 and L5, you can find positions where different influences support rather than conflict with each other, creating stability that requires minimal energy to maintain. The Lagrange points remind us that even in complex systems with multiple competing forces, nature provides locations of perfect balance. These cosmic sanctuaries demonstrate that stability and peace are not just possible, but mathematically inevitable outcomes of the fundamental laws governing reality. Across the cosmos, gravitational tides create gentle rhythms that connect celestial bodies in subtle dances spanning millions of years. These tidal forces, while capable of incredible effects over geological time, operate with the patience of cosmic clockwork, gradually shaping worlds and moons through gentle, persistent influences. Our moon's gravitational pull creates Earth's ocean tides, but this same force is slowly changing both worlds in a process called tidal evolution. The Earth's rotation is gradually slowing as tidal friction converts rotational energy into heat, while the moon slowly spirals outward, moving away from Earth at about the same rate fingernails grow, 3.8 centimeters per year. This tidal evolution has been proceeding for over 4 billion years, during which the moon has migrated from a position much closer to Earth to its current orbit. Early in Earth's history, when the moon was closer, ocean tides were enormous, and the day was only about 6 hours long. The gradual changes brought about by tidal forces helped stabilize Earth's climate and create the conditions necessary for complex life. Io, Jupiter's volcanically active moon, provides a spectacular example of tidal heating. As Io orbits Jupiter in an elliptical path influenced by the other Galilean moons, Jupiter's gravity alternately stretches and compresses the moon's interior. This constant flexing generates enough heat to keep Io's interior molten, creating the most volcanically active world in the solar system. Yet even Io's dramatic volcanism results from gentle, predictable tidal forces operating over orbital periods measured in days. The volcanic plumes and lava flows follow patterns determined by celestial mechanics, creating a cosmic ballet where eruptions occur in response to gravitational choreography played out across millions of years. Europa, another of Jupiter's moons, experiences tidal heating that maintains a liquid ocean beneath its icy surface. The same gravitational forces that power Io's volcanoes create a more subtle warming in Europa, keeping its subsurface ocean from freezing solid. This tidal energy may drive hydrothermal circulation that could support life in Europa's dark, deep ocean. Saturn's moon Enceladus demonstrates how tidal forces can create conditions for potential habitability even in the cold outer solar system. Tidal heating drives geological activity that creates geysers of water vapor and ice particles, ejected through fractures in the moon's south polar region. These plumes provide direct samples of the subsurface ocean that tidal forces help maintain. Binary star systems create tidal interactions on stellar scales, where gravitational forces between the stars gradually change their orbital characteristics over millions of years. Some binary systems achieve tidal locking, where each star always shows the same face to its companion, creating stable configurations that can persist for billions of years. Tidal forces in binary systems can also drive mass transfer, where material flows gently from one star to another through gravitational streams called Roche-Lobe overflow. This process happens gradually over astronomical timescales, allowing stellar systems to evolve through phases of shared evolution where both stars influence each other's development. Galaxy interactions also involve tidal forces operating on vast scales. When galaxies approach each other, tidal effects begin to operate long before any direct collision occurs. These galactic tides can trigger star formation by compressing gas clouds, create stellar streams by pulling stars from galaxy outskirts, and gradually reshape galactic structure over hundreds of millions of years. The antennae galaxies, currently in the process of merging, show how tidal forces can create structures of stunning beauty. Long tails of stars extend from both galaxies, pulled out by mutual gravitational attraction in sweeping curves that trace the orbital dance these galaxies have been performing for hundreds of millions of years. As you contemplate tidal forces, consider how gradual influences in your own life create change over long timescales. Like the moon's patient migration away from Earth, personal growth often happens through small, consistent influences rather than dramatic events. Tidal forces remind us that the most profound transformations often occur slowly, almost imperceptibly, through the accumulation of gentle influences over time. Stars live their lives with a serenity that spans billions of years, following predictable paths of evolution determined by their mass and composition. A star like our Sun will maintain nearly constant energy output for 10 billion years, providing a stable foundation for any planetary systems that might harbour life. This stellar constancy represents one of the universe's most reliable forms of patience. Main sequence stars achieve their stability through a perfect balance between gravitational compression and radiation pressure from nuclear fusion. For billions of years, these competing forces maintain an equilibrium so precise that the star's size, temperature, and energy output remain virtually constant. This hydrostatic equilibrium demonstrates nature's capacity for long-term stability in dynamic systems. Red dwarf stars, the most common type in the galaxy, represent stellar meditation taken to cosmic extremes. These small, cool stars burn their hydrogen fuel so slowly they can remain on the main sequence for trillions of years, far longer than the universe has currently existed. Some red dwarfs will still be shining when the Milky Way galaxy has completed hundreds of rotations around its center. The smallest red dwarfs, with masses just above the threshold for nuclear fusion, will burn for over 10 trillion years, gradually growing brighter as they age. These stars will witness the universe's expansion into its far future phases, serving as cosmic lighthouses that will guide whatever forms of life and intelligence emerge in the deep future of cosmic evolution. Brown dwarfs represent stars that never quite achieve the mass necessary for sustained nuclear fusion. These failed stars glow with the heat of their gravitational compression, cooling slowly over billions of years like cosmic embers. Their gradual cooling creates a natural thermometer that allows astronomers to determine their ages based on their current temperature and brightness. When Sun-like stars finally exhaust their hydrogen fuel, they don't die violently, but instead expand gently into red giant phases, increasing their size by factors of hundreds while maintaining the same total mass. This stellar senescence happens gradually over millions of years, allowing any surrounding planetary systems time to adapt to changing conditions. The final phases of stellar evolution for Sun-like stars involve the gentle ejection of their outer layers as planetary nebulae, some of the most beautiful structures in the cosmos. These expanding shells of glowing gas represent stellar death transformed into cosmic art, with the white dwarf remnant at the center serving as an ultraviolet lamp that illuminates the expanding gas with ethereal colors. White dwarf stars represent matter in one of its most stable possible configurations. These stellar remnants, containing the mass of our Sun compressed into a sphere the size of Earth, will cool slowly for trillions of years, gradually fading from white-hot through yellow, red, and eventually to black dwarf stars that emit no visible light but retain their gravitational influence. The most massive stars, while living shorter lives measured in millions rather than billions of years, demonstrate that even brief stellar lifetimes can achieve remarkable stability. These stellar giants maintain the same basic nuclear burning processes as smaller stars, just accelerated by higher temperatures and pressures in their cores. Binary star systems create opportunities for extended stellar evolution through mass transfer and shared evolution. Stars in close binary pairs can exchange material, allowing one star to rejuvenate while the other evolves, creating stellar relationships that can extend the active lifetime of stellar systems far beyond what isolated stars could achieve. Stellar clusters preserve snapshots of stellar evolution at different stages. Open clusters show stars of the same age, but different masses evolving at different rates, while globular clusters contain ancient stellar populations that have been evolving together for over 12 billion years. These stellar cities demonstrate how communities of stars can maintain their gravitational bonds over cosmic timescales. The spectroscopic analysis of starlight reveals that stellar evolution follows predictable patterns based on well-understood nuclear physics. The Hertzsprung-Russell diagram maps stellar evolution like a cosmic life cycle, showing how stars of different masses follow different evolutionary paths, but all according to the same fundamental physical laws. As you meditate on stellar evolution, allow the vast timescales of stellar life to provide perspective on your own temporal existence. Stars demonstrate that persistence and gradual change can create stability lasting billions of years. Like stars achieving hydrostatic equilibrium, you can find balance points in your own life where competing forces create stability rather than conflict. Invisible threads of dark matter stretch across hundreds of millions of light years, creating a cosmic web that serves as the scaffolding upon which all visible structure in the universe is built. This dark matter network demonstrates that the universe has an underlying architecture of connection that links every galaxy to every other galaxy through invisible filaments of gravitational influence. Computer simulations of cosmic evolution reveal that dark matter naturally organizes itself into a web-like structure, with dense nodes connected by thinner filaments and separated by vast voids. This cosmic web emerges spontaneously from the gravitational interactions of dark matter particles over billions of years, creating a natural infrastructure that guides the formation of galaxies and galaxy clusters. The dark matter halos that surround galaxies extend far beyond the visible stellar disks, creating invisible spheres of gravitational influence that can be 10 times larger than the galaxy they contain. Our Milky Way sits within a dark matter halo that extends nearly 1 million light-years from the galactic center, connecting us gravitationally to the nearest neighboring galaxies. This dark matter infrastructure provides stability for galactic evolution over cosmic timescales. Without dark matter halos, galaxies would be unable to retain their gas during interactions with other galaxies, and the stellar disks we observe would be disrupted by gravitational perturbations. Dark matter serves as a protective cocoon that preserves galactic structure. The local group of galaxies, including the Milky Way and Andromeda, exists within a dark matter superstructure that has been guiding the motion of our galactic neighborhood for billions of years. This invisible architecture determines the large-scale flows of matter that will eventually bring Andromeda and the Milky Way together in a gentle galactic merger billions of years in the future. Dark matter filaments serve as highways for intergalactic gas, channeling hydrogen and helium along their lengths and delivering raw material to galaxies for continued star formation. This cosmic plumbing system operates on scales of hundreds of millions of light-years, ensuring that galaxies receive the resources they need to continue evolving over cosmic time. The cosmic voids between dark matter filaments are not empty, but represent regions where matter density is significantly lower than the cosmic average. These voids, some spanning hundreds of millions of light-years across, create vast spaces of cosmic tranquility where galaxies are rare and gravitational influences are minimal. Galaxy clusters form at the intersections of dark matter filaments, like cities built at the crossroads of highways. These massive structures, containing thousands of galaxies and vast amounts of hot gas, represent the largest gravitationally bound objects in the universe. They demonstrate how dark matter architecture guides the formation of cosmic structure on the largest possible scales. The gravitational lensing effects of dark matter allow astronomers to map its distribution by observing how it bends light from more distant galaxies. These lensing studies reveal that dark matter follows the same web-like distribution predicted by computer simulations, confirming that the cosmic web is a real structural feature of the universe. Weak gravitational lensing creates subtle distortions in the shapes of distant galaxies, allowing scientists to map dark matter structure across vast regions of sky. These cosmic-scale gravitational maps reveal the dark matter web in unprecedented detail, showing how matter is distributed on scales ranging from individual galaxy halos to the largest structures in the observable universe. The cosmic web provides a framework for understanding galaxy evolution, as galaxies that form in different environments, dense cluster cores, filament intersections, or isolated voids, develop different characteristics based on their location within the dark matter infrastructure. This environmental influence shapes galactic properties over billions of years. Dark matter's gravitational influence operates democratically across all scales, from the smallest dwarf galaxies to the largest superclusters. This creates a hierarchical structure where smaller dark matter halos merge to form larger ones, building cosmic structure from the bottom up over the entire history of the universe. As you contemplate the cosmic web, imagine yourself as part of this vast network of connection. Just as dark matter filaments link galaxies across hundreds of millions of light years, invisible connections link you to other people, other life forms, and ultimately to the cosmic structures that gave birth to the elements in your body. The dark matter web reminds us that nothing in the universe exists in isolation. Everything is connected through the invisible infrastructure of cosmic architecture. Galaxies breathe on timescales of hundreds of millions of years, cycling gas between their star-forming regions and their extended halos in processes that regulate stellar birth rates and maintain galactic equilibrium over cosmic ages. This galactic respiration demonstrates the universe's capacity for self-regulation, creating feedback loops that prevent runaway star formation while ensuring continuous stellar renewal. The Milky Way inhales gas from its surrounding circumgalactic medium, drawing in fresh hydrogen and helium that provide raw material for new generations of stars. This accretion process happens gradually, with gas streams following spiral patterns as they flow inward under the influence of the galaxy's rotation and magnetic fields. The infall rates are precisely balanced to sustain star formation at levels that can continue for billions of years. Stellar winds and supernova explosions create galactic exhalation, driving enriched gas outward from star-forming regions into the galaxy's halo. This galactic fountain carries heavy elements created in stellar cores out to distances of tens of thousands of light years, where the gas cools and eventually falls back toward the galactic disk in a continuous cycle of renewal and enrichment. The timescales of galactic breathing create a cosmic rhythm that spans hundreds of galactic rotations. Gas expelled from the disk may spend 500 million years in the halo before returning, during which time it travels distances comparable to the galaxy's diameter. This extended journey allows the gas to mix with material from other regions, creating chemical homogeneity across vast scales. Satellite galaxies contribute to this breathing process by adding their own gas reservoirs when they fall into larger galaxy halos. The Magellanic Clouds are currently contributing gas to the Milky Way through gravitational interactions that strip material from the smaller galaxies and add it to our galaxy's circumgalactic medium. The hot gas that fills galaxy halos plays a crucial role in regulating star formation rates. This million-degree plasma, heated by stellar feedback and gravitational processes, creates pressure that can prevent rapid cooling and collapse of inflowing gas. The result is a cosmic thermostat that maintains star formation at sustainable levels over billions of years. Some galaxies exhibit breathing patterns influenced by interactions with their environment. Galaxies falling through galaxy clusters experience rain pressure as they move through the cluster's hot intracluster medium, creating asymmetric gas flows that can trigger star formation on one side while stripping gas from the other. These environmental effects create diverse breathing patterns across different galactic populations. Active galactic nuclei add another component to galactic breathing through feedback from supermassive black holes. When these central engines are active, they can drive powerful outflows that clear gas from central regions, temporarily reducing star formation rates. This feedback creates episodic breathing patterns where star formation alternates between active and quiescent phases over millions of years. The chemical evolution of galaxies depends critically on their breathing patterns. Elements created in massive stars must be mixed throughout galactic gas reservoirs to enrich future generations of star formation. The galactic fountain serves as a cosmic mixing bowl, ensuring that heavy elements are distributed uniformly across galaxy disks over cosmic time. Green Valley galaxies represent systems in transition between active star formation and quiescence, capturing galactic breathing in the process of change. These galaxies show evidence of recent gas expulsion that has temporarily reduced their star formation rates, demonstrating how breathing patterns can shift galactic evolution from one phase to another. Computer simulations of galaxy evolution reveal that breathing patterns are sensitive to galaxy mass, with more massive systems developing more vigorous circulation patterns. The most massive galaxies can maintain hot gas halos for billions of years, creating stable reservoirs that regulate star formation through cosmic ages. As you meditate on galactic breathing, synchronize your own breath with these cosmic cycles. Imagine inhaling fresh hydrogen from the circumgalactic medium, holding it as stars form and evolve in your stellar disk, then exhaling enriched gas into your extended halo. Allow the rhythm of galactic respiration to remind you that all systems, from biological to cosmic, maintain themselves through cycles of renewal and regeneration. In the dense cores of galaxy clusters reside the universe's most massive and serene stellar systems, giant elliptical galaxies that have achieved a state of cosmic contentment after billions of years of evolution. These galactic elders contain up to 1 trillion stars arranged in smooth, featureless distributions that speak of ancient violence transformed into present tranquility. Unlike the active spiral galaxies with their ongoing star formation and dynamic structure, elliptical galaxies exist in a state of stellar retirement. Their red and yellow stellar populations are dominated by ancient stars that formed during the galaxy's youth, when the universe was more gas-rich and star formation rates were higher. Now these systems maintain their structure through gravitational equilibrium alone, having consumed most of their gas reservoirs billions of years ago. M87, the giant elliptical galaxy at the heart of the Virgo cluster, contains over 1 trillion stars distributed across a volume larger than our local group of galaxies. This cosmic metropolis has remained structurally stable for over 10 billion years, its stars following orbital paths that create the galaxy's smooth brightness profile through pure gravitational dynamics. The supermassive black holes at the centers of elliptical galaxies have grown to enormous sizes, some containing tens of billions of solar masses, but now exist in relative quiescence. These central engines occasionally flicker to life when gas clouds fall into their gravitational wells, but most of the time they remain dormant, serving as gravitational anchors for their vast stellar systems. Giant elliptical galaxies demonstrate that cosmic systems can achieve stable end states after periods of active evolution. Like cosmic retirement communities, these systems have finished their major growth phases and now maintain themselves through the orderly motion of their ancient stellar populations. The random orbits of their stars create three-dimensional structures that resist further evolution, having reached a state of maximum entropy consistent with their gravitational constraints. The globular cluster systems surrounding elliptical galaxies contain some of the oldest stellar populations in the universe. These ancient star clusters, formed during the galaxy's early assembly phases, now orbit through the galaxy's halo like satellites around a planet. Some giant ellipticals host tens of thousands of globular clusters, creating rich ecosystems of ancient stellar populations. X-ray observations reveal that elliptical galaxies are embedded in halos of hot gas with temperatures reaching millions of degrees. This hot atmosphere, heated by stellar winds and supernova explosions over billions of years, creates a tenuous medium that glows softly in X-rays and extends far beyond the visible stellar distribution. The smooth light profiles of elliptical galaxies follow mathematical laws discovered through careful photometric studies. The Cercic profile describes how stellar density decreases with radius in these systems, revealing underlying structural regularities that emerge from the gravitational interactions of billions of stars over cosmic time. Brightest cluster galaxies, BCGs, represent the most extreme examples of elliptical galaxy evolution. These systems, which always occupy the centers of the most massive galaxy clusters, can extend for millions of light years and contain the integrated stellar populations of dozens of smaller galaxies that have merged over cosmic history. The stellar kinematics of elliptical galaxies reveal complex internal structure hidden beneath their smooth appearance. Stars in these systems follow a mixture of radial and tangential orbits, creating velocity dispersion patterns that maintain the galaxy's three-dimensional structure. This orbital complexity demonstrates that apparent simplicity can emerge from underlying dynamical richness. Some elliptical galaxies show evidence of recent minor mergers or gas accretion events in the form of stellar shells, ripples, or dust lanes. These features indicate that even these mature systems continue to evolve slowly through interactions with their environment, though at rates much slower than during their active formation phases. The evolution of elliptical galaxies involves a transition from gas-rich, star-forming systems to gas-poor, passively evolving ones. This transformation, often triggered by galaxy mergers or environmental effects, represents a fundamental change in galactic metabolism from active growth to stable maintenance. As you contemplate these gentle giants, consider how achieving stability and contentment might look in your own life. Elliptical galaxies demonstrate that systems can reach states of dynamic equilibrium where internal motion creates structure and stability rather than chaos. Like these cosmic elders, you too can achieve phases of life where past experiences contribute to present stability rather than ongoing turbulence. Ripples in the fabric of space-time itself carry information across the cosmos at the speed of light, bringing news of the most serene yet powerful events in the universe. Gravitational waves represent disturbances so subtle they change distances by less than 1,000th the width of a proton, yet they carry energies that can exceed the combined light output of all stars in the observable universe. The Laser Interferometer, Gravitational Wave Observatory, LIGO, has opened a new sensory channel for experiencing the cosmos, allowing us to hear the gravitational songs of merging black holes and neutron stars. These cosmic melodies play in frequencies similar to audio waves, creating literal music of the spheres that can be converted to sound and played through speakers. When two black holes spiral toward each other in their final dance, They create gravitational waves that increase in frequency and amplitude like a cosmic chirp. The wave pattern follows precise mathematical predictions from Einstein's general relativity, rising from frequencies below human hearing to sounds resembling a bird's call as the black holes merge and ring down to their final combined state. Neutron star mergers produce more complex gravitational wave signatures, with frequencies that can extend into the audio range for minutes before the final coalescence. These longer duration signals allow scientists to extract detailed information about the equation of state of matter at nuclear density, providing insights into the fundamental physics governing the densest objects in the universe. The gravitational wave background represents a form of cosmic ambient sound, a superposition of waves from countless merging compact objects throughout cosmic history. Future space-based detectors may be able to detect this background, revealing the integrated history of black hole and neutron star evolution across the entire observable universe. Primordial gravitational waves, if they exist, would carry information from the first moments after the Big Bang, when the universe underwent rapid inflation. These ancient waves would be stretched to incredibly long wavelengths by cosmic expansion, requiring space-based interferometers with arm lengths of millions of kilometers to detect them. The propagation of gravitational waves through space provides a clean probe of cosmic expansion and structure. Unlike electromagnetic radiation, gravitational waves pass through matter virtually unimpeded, carrying undistorted information about their sources across billions of light-years of intervening space. Binary pulsar systems create gravitational waves that slowly drain energy from the orbital motion, causing the pulsars to spiral inward over millions of years. The Hulse-Taylor binary pulsar provided the first indirect evidence for gravitational waves by demonstrating orbital decay at precisely the rate predicted by general relativity, earning its discoverers the Nobel Prize. Supermassive black hole binaries in galaxy cores will produce gravitational waves detectable by future space-based missions like LISA, Laser Interferometer Space Antenna. These waves will have periods measured in hours to years, creating cosmic rhythms that pulse with the frequencies of planetary orbits rather than audio waves. The polarization of gravitational waves encodes information about the geometry of their sources and the nature of gravity itself. Unlike electromagnetic waves, which have two polarization states, gravitational waves in Einstein's theory have two different polarization patterns that stretch and squeeze space in orthogonal directions. Gravitational wave astronomy has revealed that black hole mergers are surprisingly common, occurring at rates of dozens per year within the detection volume of current instruments. This discovery suggests that binary black hole systems form efficiently throughout the universe and that the cosmos is alive with gravitational wave signals at all times. The precise timing and amplitude of gravitational wave signals allows scientists to test general relativity in the strong field regime, where gravitational effects are billions of times stronger than any terrestrial experiment can achieve. So far, every detection has confirmed Einstein's predictions with remarkable precision. Electromagnetic counterparts to gravitational wave sources provide multi-messenger astronomy opportunities, where the same cosmic event can be studied through multiple types of radiation. The neutron star merger, GW 170817, was observed in gravitational waves, gamma rays, X-rays, optical light, and radio waves, creating the most complete picture ever obtained of a cosmic cataclysm. As you listen to the gravitational wave universe, imagine space-time itself as a cosmic musical instrument, with massive objects playing notes that propagate through the fabric of reality. Allow the rhythm of these cosmic songs to provide a soundtrack for meditation, connecting you directly to the dynamic nature of space and time themselves. In the disk of gas and dust surrounding a young star, countless microscopic grains begin their billion-year journey toward becoming worlds. This process of planetary formation demonstrates the universe's capacity for gradual construction, building complex systems through the patient accumulation of simple materials over geological timescales. The initial stages of planet formation occur in protoplanetary disks, where dust grains smaller than the width of a human hair slowly stick together through electrostatic forces and gentle collisions. These cosmic snowballs grow by accreting more material, gradually increasing in size from microscopic particles to pebbles to boulders over millions of years. In the cooler outer regions of protoplanetary disks, water and other volatile compounds condense onto dust grains, creating icy planetesimals that can grow more rapidly than their rocky counterparts in the inner disk. This snowline creates a natural boundary that determines where different types of planets can form, establishing the architecture that will characterize the mature planetary system. Planetary embryos form through the gradual coalescence of planetesimals, a process that can take 10 million years to produce objects the size of Mars. These protoplanets then undergo a phase of giant impacts that can last for hundreds of millions of years, during which their final masses, compositions, and orbital characteristics are determined. The formation of gas giant planets requires the rapid accumulation of solid cores massive enough to gravitationally capture hydrogen and helium from the surrounding disk before stellar winds disperse the gas. This process must occur within the first few million years of the disk's lifetime, creating a narrow window for giant planet formation. Rocky planets continue to grow through impacts even after the gas disk has dissipated, in a process called late heavy bombardment that can continue for several hundred million years. During this phase, water and organic compounds may be delivered to planetary surfaces by comets and asteroids, setting the stage for the later development of atmospheres and potentially life. The Nice model describes how planetary systems achieve their final orbital configurations through gravitational interactions among the giant planets. These dynamical processes can scatter smaller bodies throughout the system, populate asteroid belts and Kuiper belt analogues, and determine the long-term stability of planetary orbits. Tidal evolution continues to modify planetary systems long after their formation is complete. Planets can migrate inward or outward due to gravitational interactions with remaining disk material or with other planets, while tidal forces gradually circularize orbits and synchronize rotation periods with orbital motion. The formation of planetary moons follows similar processes on smaller scales, with material in circumplanetary disks gradually coalescing into satellite systems. The regular moon systems of the giant planets likely formed this way, while irregular moons represent captured asteroids or comets that were gravitationally bound during chance encounters. Atmospheric formation and evolution occur over billions of years as planets outgaze volatiles from their interiors, lose material to space through various escape processes, and potentially acquire new atmospheric components through impacts or stellar wind interactions. The balance of these processes determines whether planets retain thick atmospheres, thin atmospheres, or lose their atmospheres entirely. The discovery of exoplanetary systems has revealed that planetary formation can produce a remarkable diversity of outcomes. Hot Jupiters orbit closer to their stars than Mercury orbits the Sun, super-Earths have no analogue in our solar system, and some planets orbit binary stars in complex gravitational environments that challenge our understanding of planetary dynamics. Planetary system architectures preserve information about formation processes, with orbital resonances, asteroid belts, and comet populations serving as fossil records of the dynamical evolution that shaped each system. These clues allow astronomers to reconstruct the formation histories of exoplanetary systems billions of years after the process was complete. The habitable zones around stars, define regions where liquid water can exist on planetary surfaces. But the actual habitability of planets depends on many factors, including atmospheric composition, magnetic field strength, and geological activity. The long-term evolution of these characteristics determines whether planets can maintain conditions suitable for life over billions of years. As you contemplate planetary formation, consider how patient, gradual processes in your own life can lead to outcomes that seem impossible when viewed from the beginning. Like dust grains slowly accreting into worlds, small consistent actions and influences can accumulate over time to create complex, stable systems that persist for cosmic ages. Between the galaxies lies the vast majority of the universe's volume, regions so empty that entire civilizations could exist without ever detecting another galaxy beyond their own. These cosmic voids represent the ultimate expression of spaciousness, where matter density approaches the theoretical minimum and the expansion of the universe becomes directly perceptible. The typical distance between galaxies in the cosmic web is about 1 to 2 megaparsecs, but the largest voids can span hundreds of megaparsecs, distances so vast that light takes hundreds of millions of years to cross them. Within these supervoids, galaxies are so rare that an observer located at their center might see nothing but empty space in every direction, with the nearest neighbors invisible beyond the cosmic horizon. The Boötes void, also known as the Great Nothing, spans 330 million light-years in diameter and contains almost no galaxies throughout its volume. An observer located at its center would see a universe containing only about 1% of the typical galaxy density, creating a cosmic perspective radically different from our own location within the relatively dense local group environment. Intergalactic space is not completely empty, but contains a tenuous medium of gas with densities of only a few atoms per cubic meter. This intergalactic medium preserves a record of cosmic chemical evolution, containing heavy elements expelled from galaxies by stellar winds and supernova explosions over billions of years. The temperature of intergalactic gas reaches millions of degrees in the filaments of the cosmic web, heated by gravitational compression as matter flows along dark matter scaffolding. This hot gas glows faintly in X-rays, creating a barely detectable web of emission that traces the largest structures in the universe. Cosmic expansion is most apparent in intergalactic space, where the effects of local gravitational binding are minimal. Here, the Hubble flow carries space itself outward at rates proportional to distance, creating a smooth expansion field that demonstrates the dynamic nature of spacetime on the largest scales. The cosmic microwave background radiation provides a uniform bath of ancient photons throughout intergalactic space, creating a baseline temperature of 2.725 Kelvin that serves as the universe's fundamental thermal reference point. These primordial photons have been traveling freely through space for 13.8 billion years, filling every cubic centimeter of intergalactic volume. Intergalactic magnetic fields, though incredibly weak, thread through cosmic voids with field strengths billions of times weaker than Earth's magnetic field. These fields may preserve information about magnetic seed fields from the early universe, providing clues about magnetogenesis during cosmic dawn. High-energy cosmic ray particles travel through intergalactic space with minimal interference, creating a sparse but detectable flux of relativistic nuclei that carries information about the most energetic acceleration processes in the universe. These particles can travel for billions of years through intergalactic voids before encountering significant material. Gravitational waves propagate freely through intergalactic space, carrying information about merging black holes and neutron stars from cosmic distances. The emptiness of intergalactic space allows these ripples in space-time to travel virtually unimpeded, preserving the detailed signatures of their sources across billions of light-years. Dark energy dominates the energy density of intergalactic space, creating the mysterious force responsible for accelerating cosmic expansion. This invisible energy component makes up about 70% of the universe's total energy budget, yet its nature remains completely unknown despite its overwhelming cosmic importance. The cosmic web's evolution creates increasingly large voids as structure formation continues, with matter flowing out of underdense regions and into the filaments and nodes where galaxies form. This process gradually increases the emptiness of intergalactic space, making voids larger and more isolated over cosmic time. Observations of distant quasars reveal that intergalactic space has become increasingly transparent over cosmic history as the universe reionized following the Dark Ages. This cosmic clearing process allowed light to travel freely through previously opaque regions, opening up intergalactic space to radiation from the first stars and galaxies. The philosophy of intergalactic space offers profound perspectives on scale, emptiness, and cosmic context. These vast regions remind us that matter and structure, while fascinating in their complexity, occupy only a tiny fraction of the universe's volume. The overwhelming majority of reality consists of space itself, expanding and evolving according to laws we are still working to understand. As you meditate on intergalactic emptiness, allow yourself to experience the vastness of cosmic space. Imagine floating in a supervoid where galaxies are so distant they cannot be seen, where the cosmic microwave background provides the only company, and where the expansion of the universe becomes a directly perceptible reality. Let this ultimate spaciousness provide perspective on the relatively dense, interconnected nature of terrestrial existence. We have journeyed through scales that span from quantum fields to cosmic voids, witnessing forces that demonstrate the universe's fundamental tendency toward balance, connection, and gradual transformation. From the patient pulse of distant pulsars to the vast breathing of galaxies, from the gentle formation of planets to the serene expansion of intergalactic space, we have seen that the cosmos operates according to principles of harmony rather than chaos, patience rather than urgency, and connection rather than isolation. The universe reveals itself not as a collection of separate objects, but as an integrated system where quantum fields connect all matter. Gravitational waves carry information across cosmic distances. Dark matter webs link galaxies across hundreds of millions of light years, and the cosmic microwave background bathes everything in the afterglow of creation itself. Your own existence participates in this cosmic symphony. The calcium in your bones remembers its stellar birthplace. The iron in your blood carries the signature of ancient supernova explosions. The hydrogen in your water molecules preserves information from the first minutes after the Big Bang. You are not observing the universe from outside. You are the universe expressing itself in conscious form, a temporary arrangement of cosmic material that has organized itself into awareness. The timescales we have explored, from microsecond pulsar rotations to billion-year galactic cycles, provide perspective that can transform anxiety into acceptance, urgency into patience, and isolation into connection. When viewed from cosmic scales, personal concerns become not insignificant, but rather part of the natural process by which the universe continues to organize itself into ever more complex and beautiful forms. The forces that shape galaxies also shape human experience. Tidal forces that slowly change planetary orbits mirror the gradual influences that transform personal growth. Gravitational equilibrium points that create stable sanctuaries in space reflect the balance points that create stability in human systems. The patient formation of stars and planets demonstrates that the most profound transformations often occur through small, consistent influences rather than dramatic events. The cosmic web of dark matter that connects galaxies across vast distances serves as a metaphor for the invisible connections that link human lives to each other and to the larger systems of which they are part. Nothing in the universe exists in isolation. Every particle, every star, every galaxy participates in the larger network of cosmic evolution. The universe's expansion, driven by dark energy, reminds us that change and growth are fundamental characteristics of reality itself. Just as space creates more of itself as it expands, consciousness can grow and develop in ways that seem to create new possibilities rather than simply rearranging existing ones. The gravitational waves that carry information across the cosmos demonstrate that events in one region of space affect all other regions, creating a universe where everything is connected through the dynamic fabric of space-time itself. Your thoughts, emotions, and actions participate in this cosmic connectedness, contributing to the ongoing evolution of reality. As we conclude this journey through cosmic serenity, remember that the same forces that created and maintain galaxies, stars, and planets are also maintaining you. The strong nuclear force continues to hold your atoms together. Electromagnetic forces maintain the chemical bonds that allow your cells to function. Gravity keeps you connected to the Earth, which orbits a star that participates in the rotation of a galaxy that moves through space as part of the cosmic web. You exist at the intersection of all cosmic forces, in a moment of space and time that represents the current phase of the universe's 13.8 billion year journey toward greater complexity and awareness. The atoms in your body have been on this journey since the first stars formed, and they will continue their cosmic travels long after your current arrangement dissolves back into the cycles of stellar birth and death. The universe demonstrates that patience, gradual change, and natural balance create stability that can persist for billions of years. By aligning yourself with these cosmic principles, accepting the natural rhythms of growth and change, recognizing your connection to larger systems, and trusting in the fundamental processes that have been shaping reality since the beginning of time, you participate consciously in the ongoing creation of cosmic harmony. Let the serenity of space remind you that you are held by forces older and more reliable than any temporary concern. The universe has been working for nearly 14 billion years to create the conditions necessary for your existence, and it will continue its patient evolution long after your atomic constituents have been recycled into new forms of cosmic beauty. In understanding cosmic serenity, you discover that peace is not the absence of change, but rather alignment with the natural processes of transformation that characterize all existence. The universe itself provides the ultimate model for achieving harmony within change, stability within growth, and connection within the vastness of space and time. You are, quite literally, made of stars. And in recognizing this cosmic inheritance, you join the universe in its eternal dance of creation, transformation, and transcendence. The cosmos is not something you observe, it is something you are, expressing itself through your consciousness as part of its ongoing journey toward ever greater understanding of its own infinite nature.